If it hasn't happened to you, it's probably happened to a friend. The painful moment of watching a phone fall. But why does it fall? What determines the pull on it, and how big is that pull? In this video, you'll start to learn the answers to these questions through the law of gravity. After completing this assignment, you should be able to understand the structure of the formula for gravitational force, calculate the gravitational force, and relate gravitational forces to the acceleration of an object. A solid understanding of Newton's second law will help you get the most out of this video. Understanding gravity is important because it is an attractive force between all matter in the universe, from the gigantic, like planets or galaxies, to the small objects in our everyday lives. And it mediates some transformations between kinetic and potential energy. You interact with gravity every day, but may not have thought systematically about it. Now consider, is the gravitational force between the phone and the man greater than, equal to, or smaller than the gravitational force between the phone and the Earth? The correct answer is that the gravitational force between the man and his phone is less than the gravitational force between the phone and the Earth. From your own experiences, if your gravitational pull was stronger than the Earth's pull, objects wouldn't fall away from you. The Earth, at 5.98 times 10 to the 24th power kilograms, is much more massive than a person in the 50 to 100 kilograms range. The Earth's mass exerts a correspondingly larger gravitational force. But the mass of the Earth isn't the only factor. The person has more mass than the phone. Your own experience tells you that it's easier to pick up a phone than a person. The person weighs more because Earth's gravity pulls on them more than it pulls on the phone. Now consider the Sun, which also pulls on you and is over 300,000 times more massive than the Earth. As the Earth rotates, sometimes the Sun is on the far side of the Earth, and sometimes it is above you. Think about how your weight feels during the day versus at night. Is the gravitational force between you and the Earth greater than, equal to, or smaller than that between you and the Sun? The correct answer is that the gravitational force between you and the Earth is much greater than that between you and the Sun. You don't fly off the Earth when the Sun is overhead. In fact, the Sun's pull on you is so small, you don't even notice a difference in your weight between daytime and nighttime. Why is that? Even though the gravitational force Fg is proportional to the product of the two masses involved, m1 and m2, it also gets smaller as the separation r between objects increases. Experimentally, scientists have determined that the force of gravity is inversely proportional to the square of the distance between the objects. Let's review what we've determined so far. The force of gravity is proportional to masses of the two objects times each other, and it's proportional to the inverse square of the distance between them. We combine these two relations with a constant, capital G, to incorporate the proportionality. This equation is Newton's law of gravity. The constant, capital G, is the gravitational constant and has a value of 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. That value is so small that large masses like planets are needed for moderate gravitational forces. The gravitational constant, capital G, is a fundamental constant of the universe. This law describes the forces on planets orbiting our Sun as well as here on the Earth. The force of gravity between two objects is inversely proportional to the square of the distance between them. We measure their separation between their centers of mass. Most of the time, we don't notice the force of gravity changing because our motion is so much smaller than the radius of the Earth. Even a mountain higher than Everest is pretty small potatoes compared to the radius of the Earth. Using Newton's gravity equation, we can calculate the force from Earth on an object of mass m near Earth. We'll use m for m2. We plug in the value of g, the mass of the Earth as m1, and the radius of the Earth as r. Simplifying the equation gives us a result of 9.8 meters per second squared times the mass m of the object in question. If gravity is the only force acting on the object, then F net, which is equal to the mass times the acceleration of the object, is equal to the gravitational force between the Earth and the mass. And the force from Earth on a mass m is 9.8 meters per second squared times the object's mass, which means that independent of the object's mass, the free fall acceleration near the Earth is always 9.8 meters per second squared. This is a reduction of our general equation, but it allows you to predict the force of gravity and the resulting acceleration near the Earth. This value should look familiar since it is the same value you've been using for the acceleration due to gravity up to this point in your course. In general, the free fall acceleration small g for a planet equals capital G times the planet's mass divided by the square of its radius. Okay, let's recap the key aspects of Newton's law of gravity. The force of gravity depends on the quantities of the two masses involved and the distance between them. It can be written generally as Fg equals capital G times m1 times m2 divided by r squared, where capital G is a fundamental constant of the universe and has a value of 6.67 times 10 to the negative 11th with units of Newton meters squared per kilogram squared. Near the surface, the force of gravity from the Earth on a mass m is 9.8 meters per second squared times the quantity of mass it is acting on.